Hello. Today I was going to go through the last topic for Genetics Colloquium 2, and that is reading and interpreting karyograms. Now, what are karyograms? They are pretty much I would say, assortment of all of our different chromosomes in our body. So this is how a normal karyogram will look like with a normal karyotype. Karyogram is just the name for an image that looks like this, while karyotype is what our assortment actually looks like of our chromosomes. So in here you can see normally we have a pair or 23 pairs of chromosomes, 22 which are non-sex chromosomes and 2 which are sex chromosomes. So either this XY or XX right here. And another important note is to just be able to notice that each of these pairs are equally as long. Yes, they are kind of asymmetrical. They don't really look exactly like one another. However, again, it's very, very important to note that they're all at an equal length. And that is what's going to help you be able to distinguish normal chromosome pairs from abnormal ones. So our first rule, we have actually 4 different types of chromosomal aberrations or phenotypes that we are going to be covering in our karyograms that we have to identify from the karyograms. The first one is deletion, but there's also insertion, translocation, reciprocal, as well as Robertsonian translocation. Now I'll go through each and every one of them, but let's start with the easy one. Deletion. A piece of a chromosome is missing in the karyotype. So this is written with a D or a del, and I will soon show you how. So for example, we have this karyogram right here. Now I took away the arrow that would signify to which chromosome this would be, just so that it would be easier for you guys to kind of identify it without the arrow, because according to our professor, we might not have an arrow that points immediately to the wrong or to the abnormal or chromosomal aberration. So this is just a little bit of a practice for us. So let's look through each and every one of these chromosomes. We can see here that these look pretty much equal lengths. So does these are also equal lengths. These are also, but once you get to chromosome pair number 5, you can see that one of the chromosomes is actually shorter than the other chromosome. This is what we call a deletion. So it only affects one chromosome pair. Please keep that in mind. Deletion and insertion only affects one chromosome specifically, not several. That would be incredibly unique. But with Colloquium 2 of Genetics, we're only looking at one chromosome that is being deleted or inserted. When it comes to reciprocal translocation as well as Robertsonian translocation, that's going to be 2 chromosomes affected, but for deletion and insertion, only 1. So if you compare with all of the rest, all of them being equal lengths, just like they are here, just like they are here, of course X and Y is different, that is completely normal, then we know for sure that, okay, this has to be deletion, because only this little area is what's abnormal about this whole set, right? So in this case, let me write down the karyotype for this person. First of all, how many chromosomes do they have in total? Of course, you know, with 22, that means 44 here, and then 45, 46, so it would be 46. And then what sex chromosomes do they have? They have an X and a Y. So we would write that down as well. And then what kind of chromosomal aberration do they have? Now we know it's deletion on 5, and we write deletion with a D or a del. So D and then apostrophe, not apostrophe, parentheses. We write the number of the chromosome pair that is affected. So it would be number 5 here. So we write down 5. Also, excuse me if you hear my stomach gurgling. It does that sometimes. All right, and that is the karyotype for this individual right here. Done with that already. let's look at another example right here. Now this one I also took away the arrow, but it is a little bit more trickier to see because all of these are pretty noodly in shape, so it's hard to distinguish if they're different at different lengths or not. Actually, this one looks different from this one, so I would also go with this being the abnormal one. However, in our case, according to the source that I got this image from, it's actually chromosome pair number 4. But 13 wouldn't be that bad of an answer either. I would actually probably go more for 13 than 4. But let's go with the source, what the source says, which is 4 right here. None of the other chromosomes are affected because they're all at an equal length pretty much. So we write down the amount of chromosomes that we see, and we see of course 44 right here, and then plus 2 here, so that would be 46. And then we write down the 6 chromosomes, which are these 2 right here, so they have 2 in X, so it would be X, X. And then where the deletion is, so it would be D4 in this case, because in this case the source says that there has been a deletion right here. That easy. So you can see here, this is just a graphical, how do you say, a horrible representation of me trying to draw what a chromosomal or what a deletion looks like. So you can see the first pair here, and then the second pair, you can see here that a piece is missing compared to the normal looking ones right here. All right. I feel like I should say something else, but let's carry on. Oh yeah, for deletion and for insertion, as well as translocation reciprocal, we'll get to that, but they will always have 46 chromosomes in every karyotype. Always, always, always. But we will get to that and you will understand why soon. So here, insertion is a piece of a chromosome that is added in the karyotype, written with I or ins. So let's look at here. So the chromosome will look larger, as you see here in my amazing, beautiful representation. The chromosome should end here, but there has been an insertion of something, an insertion of an extra piece, you could say. So if we carry on looking here, it could take you a while. Also, 14 is missing. There should be another one right here. I don't know why it's missing, but just imagine that there is one right there, right? I know why it's missing, because this is supposed to be Robertsonian, but please ignore that this is actually a Robertsonian and just imagine that this chromosome exists right here. So what do we have here? We actually have a insertion right at chromosome pair number 13. Why? Because all of these look approximately equal length to one another right here. However, when we get to 13, it has this extra little piece right there, which again looks very Robertsonian-esque, but please ignore that that there's no chromosome right here. There should be. Actually, if I, oh, okay, well, as you see, according to the source, this was supposed to be the insertion. I googled it and it was supposed to be there, but apparently it's not. But just imagine that this is the insertion and there's an extra chromosome right here. Okay, so amount of chromosomes in this image would be 46 always for insertion and deletion. And then the type of 6 is XX. So we would write X, X, and then we would have a write the parentheses, but before the parentheses we have to write if it's insertion and deletion. And we write an I and then 13th, because that's what chromosome pair or chromosome is being affected. Next up is this one right here, and I think you can see immediately which one is the inserted chromosome. It's pretty easy to notice, but if you need to take a while, well, actually pause it right here because I'm just going to tell you guys the answer. it's of course chromosome pair number 10. Why? Because you can see this big, almost tail for this chromosome right here. So that's why we know for sure that this is an insertion and not anything else, because we still have 46 chromosomes, okay? It's very important that if you see an addition somewhere or a deletion somewhere, just like you do right 5 right here, it's an insertion and deletion only if we have 46 chromosomes in each, okay? Otherwise, you're probably looking at some sort of Robertsonian translocation. But anyways, let's write down the karyotype here. We know we have 46 chromosomes, and then we have an X and Y chromosome right here. And then we have to write in the insertion, so it would be a I, and then parentheses, the one that's being affected, so that's number 10. Okay, that was insertion, very easy, deletion and insertion. Now we come to translocation. Now translocation is a little bit different. So you can see here we have 2 chromosome pairs instead of 1 that is being affected. From 1 chromosome pair, it loses a piece of itself and it gives it to another chromosome of another chromosome pair. So it's almost like, so one is longer while the other one's shorter. You can almost equate it to deletion and insertion. Deletion and insertion, because one seems to have something inserted while one seems to have something deleted. So that's why it's very important that when you're looking at these karyograms, that even though you're seeing something that's obviously been deleted, just like you have right here, this piece has been deleted, you have to make sure that no other chromosomes are being affected in any way, because from here you can see this has been, well, let's see here. Oh, sorry, this has been inserted, not deleted. So here we have insertion and here we have deletion. That means that this piece has migrated down to this piece. And that's why we have translocation here and not just a simple deletion or a simple addition or insertion. So be very careful that you don't mix it up with deletion and insertion. If it only affects 1 chromosome pair, then it is deletion or insertion. If it affects 2, then it's some sort of translocation, either it be Robertsonian or reciprocal. All right, so how do you write this one? You use a T before the parentheses. So what you do here, this is also going to be 46 chromosomes, and then 46 chromosomes, and then the sex would be XX, XX, and then you write a T before for translocation, and then parentheses, the 2 chromosomes that are affected. And usually you do this in numerical order, so you start with the lowest number and end with the highest number. So it would be 6. If you can't see, this is a 6, and then a 16 right here. So that's how you write for that one. The next one, how you read this. This has also been pointed out for us. So you can see here that this is very much longer than this chromosome right here, while this chromosome right here is shorter than this chromosome right here. So this has been deleted, so a piece of this has been translocated to this chromosome right there. So that's why we have to write, of course it's still 46 chromosomes if you count them all in, and then the sex will be XX, XX, and then you take T, parentheses, you start from the lowest lowest number, which is 4, and then you end it with the highest, which is 6. So that's translocation. For reciprocal, we're going to get to how you calculate for gametes as well, but that's later on. Robertsonian is the most difficult of them all, so please pay attention when we come to Robertsonian translocation. We write it with a Rob. So how do you explain Robertsonian the best? It's a chromosome that morphs together with another, pretty much, or a chromosome that morphs together with a Yeah, with an order. I would say it. And there's a signifier for Robertsonian translocation. This is a pretty big signifier, and that is that it has one lonely chromosome. Now you will not see a lonely chromosome for a chromosome pair anywhere. Anywhere. No person has one less chromosome than they should have, because that's not viable for life. And if you develop such an embryo, it will most often leads to miscarriage. So as soon as you can see in these two karyotypes right here, one lonely chromosome in these pairs right here, you will know for sure that it is Robertsonian translocation. Okay, that is the signifier for Robertsonian translocation. Now I'm very suspicious about Robertsonian translocation for colloquium, because I feel like it's a bit harder than the rest, or calculating for the rest of the chromosomal aberrations, that we must have at least one of these in our colloquium. It's just a very, very, very big hunch in my opinion. So please make sure that to remember that if you only see one lonely chromosome, it's probably due to Robertsonian translocation. Now, what is it that happens here? So this is where we have normal chromosome pairs, right? And this only works for acrosomal chromosomes. So only on acrosomal chromosomes, which would be 13, 14, 15, 21, 22, or Y. You can ignore Y right now, because this is not something that we're going to go through in our colloquium. But for these ones, as soon as you see lonely chromosomes on these numbered pairs, then you will know for sure that it's probably Robertsonian. So here you can see it on 14, that matches. And here you can also see it on 14, which matches. But also the one affected would be 13. Which matches this and this. Okay, so what is it that happens? Acrosomes have very small, I think it's called P arms. Oh God, it's either P or Q, but I'm pretty sure it's P. Please correct me if I'm wrong. But they have very short top arms, you could say. Now what happens is that the bottom of one of these chromosomes will be migrating into the top of another chromosome, and it will get rid of this tiny arm right up here, get rid of it so that it can make room for this thing right here, and the tiny arm will create this thing right here, which is formed by it will be the rest product of what is left here after this thing has migrated. So you can say that the long arm migrates to another chromosome that also has the long arm, and both short arms of these chromosomes will kind of morph together right here, creating this, and this will be deleted because it's so unimportant. Like, we don't care about this, we're going to delete this. However, the long arms are super important. So once this migrates here and it forms like this thing right here, this counts as 2 chromosomes. Even though it's technically not a chromosome, it will count as 2 chromosomes because it has most of the information that has been given by this thing right here. So even though you will assume, well, when a person has this, we're deleting these pieces of chromosomes, it has to be an unhealthy person, that's actually not true, because the important genetic information is stored in these big arms. So if these big arms are left in the karyotype and the small arms are just deleted and exited, it's not going to make any difference on the person's pathology. So let's look at right here. We have this lonely chromosome right here. You can kind of compare it with this thing right here. And then we have this bigger chromosome right here next to 13, which you can compare with this right here. Now, this is pretty much chromosome number 14, the other one right here. So the information that we had here is just migrated right here, and this counts as almost 2 chromosomes, or information from 2 chromosomes at least. So this is enough for a person to be healthy. They just need this, this, and this. That's enough. Same thing here, the 14. It's the same chromosome pair. The chromosome would be here, but it migrates right there on the top, and it creates this bigger one. So let's write down the karyotype in our case, and please make sure to remember this. For Robertsonian translocations, for a normal karyogram for Robertsonian, you will have a total of 45 chromosomes, not 46. Even though this technically counts as 2 chromosomes, it's also not technically one chromosome. It's like a chromosome conjugate or derivative. But you will count this as one chromosome, and this is one chromosome, and this is one chromosome. So we're technically saying that there's no chromosome here, but because it's Robertsonian translocation, it's okay because it kind of lives on top of this one right here. So we can count it if you want to. This would be 1 chromosome, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. I made a mistake, probably. What am I doing? 35, 36, 37, 38, 39, 40, 41, 42, 43, 44. Okay, I made a mistake somewhere. Let me count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 45. Okay, so it's 45 chromosomes. You can count it if you want to, but it's enough to know that all of these chromosomes have a pair except for this one that has one single. So it would be 46 minus 1, and that's 45. Now, what are the six chromosomes here? And it's X and Y, so we write it down. And then for Robertsonian, you write rob before the parentheses because we're robbing a chromosome, right? And then the parentheses, and then the chromosomes that are affected in numerical order. So it would be 13, 13, comma, 14. And the same thing is for here. It even has the same X chromosome. Because it's both 13 and 14. So it's the same here, the same written karyotype. Okay, and here is also how I'm trying to describe it. So you're losing technically a chromosome here, but it's fine because it's all the information is stored here anyways. It's just morphed into one big mega chromosome. And again, this only works on chromosomes 13, 14, 15, 21 and 22. Let's ignore Y for now, but it does work on Y. But let's ignore it because it's not relevant for a click. Robertsonian translocation. This is a specific, obviously this was also Robertsonian translocation. I don't know why I wrote a 4 there. It's supposed to be, but let's just write a 4.5 because it's still about the same subject. But an important note here is that this Robertsonian translocation doesn't have to necessarily occur within 2 chromosome pairs. Like it doesn't have to occur here and here. It can occur within just 1 chromosome pair, and this is how it would look like. So let's look at this chromosome chart here. We can see right here that we only have 1 chromosome, and we know of course that has to be Robertsonian translocation because the only chromosomal aberration that only gives us 1 chromosome in a pair would be Robertsonian translocation. But then that additional chromosome has to, be migrating into some other chromosome, creating this mega chromosome, right? So let's look right here. So we have this single one right here, but none of these chromosomes right here have an additional piece, and it's a pretty large one at that, that has been added on top of one another. And of course, we're not interested in Y right now, so let's not look at Y. Instead, if we compare 14 with its neighbors, 13 and 15, we can see that it's much larger. So what happened here is that we had two chromosomes. Let's just make them look like small chromosomes. One of them, oh wait, they have to have short acromeres. So they have to look like that. One of them kind of morphed together with the other. So this one morphed together with this one right here, creating this mega chromosome and getting rid of this right here. And that is what we have here. And the signifier for it would be one single chromosome, plus that it is extremely larger than the rest of the chromosomes, in addition to the fact that none of the other chromosomes have an added like a chromosome arm added to them. So it's only 14 that's been affected. In this case, you would write it as 45, because remember that we only have one chromosome technically here, so it would be one less chromosome. And then the 6 types, which is X and Y, just like we have right here. And then Rob, parentheses, 14 and 14. Because this 14 and 14 shows us that something has happened internally between these chromosomes within this one and the same pair. Okay, now we come to knowing if a person is healthy and unhealthy depending on their karyotype. So these are the different types of chromosomal aberrations that we're going to look at. Now we're going to look at knowing if they're healthy or not. So a person is healthy if, a person is healthy if they have a balanced karyotype. What does that mean? That means that no genetic information is lost or gained. Remember that. So that would be either reciprocal translocation and Robertsonian translocation. So not deletion and not insertion. Why? Because a healthy person has to have a balanced karyotype, and that means that nothing is lost and nothing is gained. If we look at let's first look at translocation right here. You can see that nothing is lost here technically. This piece has just migrated, this piece has migrated down to this piece. So nothing is lost in this whole karyotype, because we just have a little tiny migration. They're just traveling locally pretty much. And the same thing is with Robertsonian translocation. Even though it may seem that because we have 45 chromosomes instead of the normal 46, we're losing one chromosome and therefore there is a loss, right? But not really, because this other pair of this chromosome right here has just migrated into this bigger pair. So therefore, when it comes to translocation, we are not losing anything. It's just been migrating into another part of the chromosomes. But when we come to deletion and insertion, here we can see properly that we have lost a piece without it being inserted anywhere or migrating anywhere else in this karyogram. So therefore, we've lost a piece of information. Same thing with insertion. We've gained a piece of information. And remember, you're unhealthy even if you gain an additional piece of information. It's still not good. Just because people have an extra chromosome doesn't mean that they're healthy, right? Well, they're actually unhealthy. So you can see here that they're gaining a piece of a chromosome. That means that definitely this will be unhealthy and this will be unhealthy as well. So deletion will be unhealthy, insertion will be unhealthy, but any type of translocation, whether it's reciprocal or Robertsonian, means that it's just going to be healthy. The pieces of information aren't lost, they're just migrating to other parts of the chromosomes. So that's why we know that reciprocal translocation as well as Robertsonian translocation are healthy, while unhealthy would be anything lost or gained, which is of course deletion or insertion, which we just talked about, but also trisomies. Trisomies. So trisomies, and this is only for some specific trisomies. Remember, most trisomies and monosomies. Also, what are trisomies? Let me explain. Trisomies are an additional chromosome in the chromosome pair. So for example, here in 11, if we have this additional chromosome, this would be a trisomy. We have an additional chromosome and it is creating this triplet of a chromosome instead of a duplicate, right? But in this case, if we had a trisomy on 11, it would lead to a miscarriage. It would not be viable for life. The only trisomies which are viable for life are Edwards syndrome 18, Down syndrome 21, or Pateau syndrome 13. Now I will explain to you how that would look like. Edwards syndrome, let's just look at the normal karyotype. Edwards syndrome would have, I think it was 18, let me double check. Yeah, it would have an additional chromosome in number 18 right here. So it would look something like this with a trisomy right here. While Down syndrome would have one in 21, so it would look like that. Meanwhile, Pateau syndrome would have it on 13, so it would look like this. Now you don't have to know this or like how it looks like in regards to the karyogram. The only thing you have to know is the fact that only 13, 21 and 21 and 18 trisomies are viable for life, but they will be unhealthy. In the case of Pateau and Edwards syndrome, they will be extremely unhealthy. So it's important to note, when I'm talking about unhealthy, I'm not talking about people that have gone through miscarriages or unviable, not people, but fetuses that are going through miscarriages or unviable for life, viable for life. I'm talking about the ones that are viable for life, that will be born, but will be extremely unhealthy. So let's go down again. So a person is unhealthy if they have deletions, insertions, and they have trisomies, but only in these areas. So 18, 21, and 13, you have to know this, because when you're writing the gametes or possible gametes for some karyotypes, you have to know if that gamete would be viable for life, if it would lead to healthy offspring or unhealthy offspring. So in this case, it would be viable for life, but it would be unhealthy. We'll get to examples later. 7 is miscarriages, which are non-viable for life gametes. And in this case, if they, for example, I need to make sure, if they, for example, asks for how many children would be healthy children, or what is the chance for a healthy child, and you have two options. Why am I? Excuse you. You have two unhealthy options, or not options, but possibilities. You can either get, for example, Edwards syndrome or a deletion, we could say, and then you have two healthy ones, and then you have 4 non-viable for life or miscarriages. In this case, the miscarriages don't even count, because when we're talking about what is the chance for a healthy child, we have to make sure that the child is actually born. So a fetus that is going through a miscarriage isn't technically what we would assume would be a child, right? Instead, we're looking at those born, or possibility for them to be born, viable for life. And what is the probability here? It would be 1/2 for a healthy child, because there's two unhealthy and 2 healthy, so it would be 1/2. But we'll get to that later. I will explain it more in detail. That's just a little bit for you guys to think about currently. There's no Z here. Thank you. So a miscarriage would be, in this case, any monosomy, one less chromosome. Now, how would a monosomy look like? If we look at a normal karyotype, let's imagine that this is an eraser. So a monosomy would be one less chromosome. So for example, 16 here or 21 here, you would never, ever, ever, ever see a karyogram of a monosomy, because in order to do a karyogram, that person has to be alive. And a person that is non-viable for life, you can't make this. So any, fetus or developing zygote that has a monosomy with just one chromosome in one pair will not be viable for life, and we will not get the karyogram. But it's important to know that it will immediately lead to a miscarriage. But again, remember that it is not the same as Robertsonian translocation, because Robertsonian translocation isn't technically missing the chromosome, because realistically it's just put right here. So again, just make sure to remember that, because we will never ever get a karyogram of a monosomy individual, because they will never be alive to begin with, and in order to get a karyogram they have to be alive. That's just a little bit of extra information for you guys. And then, of course, almost all trisomies, which would be one extra chromosome, except 13, 18, and 21, which is Edwards syndrome, Down syndrome, and Pateau syndrome. So these are viable for life, meaning they will be born. That doesn't mean that they will be healthy, but they will be born. And then, except for these, all other trisomies with one extra chromosome will lead to a miscarriage. Okay, now how does gametes work? So let me just tell you guys what our professor said that we're going to have in our colloquium. So we're going to have a karyogram right here. So we have chromosomes right here, right? Hello? Boop, 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 boop. Oh, I hit that. Okay, we have a karyogram right there. There's going to be 3 questions asked in total. Number 1, what karyotype is this person right here? Number 2, is the person healthy? Healthy or non-healthy? And then number 3 is going to be the last and final question, which is possible gametes, or name or write all possible gametes for the person, and write chance for them. Oh, shoot. Chance for them to be a healthy child. Okay, so those are the 3 that are going to pop up. We already know how to decide a karyotype. We've already gone through it here, right? That is the karyotype for each and every one of these. If the person is healthy and unhealthy, we know it's healthy if it's a reciprocal translocation or Robertsonian translocation. It's unhealthy if there's any deletion, insertion, or trisomies, these trisomies involved. And then write all possible gametes is the final one, and that's what I'm going to go through here. So what are gametes exactly? Gametes are our sex cells, and they will contain half of our genetic information. That means half of our normal karyotypes, or half of our chromosomes, sorry. So if we normally have 46, the gametes will have 23. Why? Because when we have a sperm here, that's the male gamete, and then we have an egg here, right? This egg will contain 23 chromosomes, will always be X, and this sperm will also contain 23 chromosomes. So when these two converge, they will create 46 chromosomes. So that is what a gamete is. So it always has to have half of what the genetic information of the parent has. So let's start with what gametes would look like for insertion, deletion, reciprocal translocation, as well as Robertsonian translocation, which is going to be a little bit more difficult than the rest, right? So for a person with insertion, remember, a person with insertion looks something like this, where they have an additional piece of a chromosome inserted into the whole, and it's just one pair that is affected. So just one chromosome that's affected right there. In our case, I drew it as this little green thing right here. All right. So there are a total of 2 options of gametes for this type of karyotype. You can either have 23X. Well, in this case, I used X. It could also be XY. So remember that all of these options can technically be Y instead of X, because again, you only have one sex chromosome in a sperm cell or an egg cell, because you have half of the genetic information of your parent. To shorten things up, I drew this inserted piece right there. And can you change the color of these? I saw someone have pink, and I kind of want to have pink. I think that it's only red. All right. In insertion case, only one chromosome is affected. So as long as you don't have this chromosome, you're going to be good, because, you know, we're going to, one type of a gamete will only have the healthy pair or pairs of chromosomes. So we will have this red one instead of this blue-green one, right? While the other option is going to actually have the blue-green one. So there's a 50-50% chance for these gametes, right? They can either get this one or this half, or they can get this half. And that is what I'm trying to represent by these 2 options right here. So the first would be healthy because there's no insertion, even though number 9 is the one affected. We're not taking the affected chromosome with us. We're taking the unaffected chromosome with us. So we're actually healthy right here. Meanwhile, for option 2, it would be 33X, which is the X chromosome, and then insertion on number 9. And now we have taken the unhealthy chromosome with us. These don't all have to be blue. It's just to represent, you know, that we're taking the other half versus the first half, right? So here we took the inserted chromosome. So this person will be unhealthy. Why? Because let's say this is an egg right here, and this egg has a inserted chromosome right here that has an additional little piece. Then the sperm that comes, if it's healthy, let's say the sperm is 23Y, if we add it with, well, actually, let me draw this. We have a sperm right here, and it's 23Y. And if we add it with this egg gamete karyotype, it would actually be 23 plus 23, which is 46. And then the sex chromosomes, which is XY, but we will still have this inserted chromosome. We will just have one right here that's normal instead, but this one will still exist. So we will still have the insertion in number 9. And that means that this person, if they're viable for life, but they will be unhealthy if they are born. So in case for insertion gametes, this is correct all the time, no matter which chromosome that is affected. It could be 10, it could be 4, it could be 3, 1, it doesn't matter. But whichever chromosome that's affected, there's either an option that the person gets the other healthy chromosome in the chromosome pair, just like this one right here, or the unhealthy one. So there's always 1 in 2 chance that the gamete produced is a healthy gamete versus an unhealthy gamete. Next up is deletion, and it works in a similar manner. So here we have number 9 I used again, and it has this piece deleted from itself. So we either, see, I'm being an idiot. I don't know why I did that. Well, actually, let's just switch this one with this one. That would make more sense. It's not color coordinated anymore, but it will make more sense. So we will either get this healthy chromosome from the chromosome pair in our gametes, which will lead to a healthy gamete, no issue at all, or we will get the unhealthy one that has the deletion upon itself. So that would lead to unhealthy, and that would be deletion and not insertion. Thank you, Nadia, for copying and not changing. So in our case, we would again, just like we had with insertion, have one healthy option as well as one unhealthy option. So the number of the chance for a healthy child will be 1/2. For reciprocal translocation, this one has 4 options in total, and I will explain why, okay? Let me just delete this thing right here. So right here, reciprocal translocation means that we've taken a piece from one chromosome and we put it upon another chromosome, okay? So in this case, it would be 8 and 9 that is affected. So we can either have a healthy option where instead of taking this big one here, we're taking this normal chromosome here and this normal chromosome here. So we're not taking either of the unhealthy options right here, right? Or unhealthy looking. This is still a healthy person because no information is gained and no information is lost. Why? Because this information that is lost here is just migrating to another piece. So nothing is gained and nothing is lost. It's just a net of 0, right? But we can still have a normal karyotype for gamete by just choosing this one and this one instead of this one and this one. So in that case, it would be 23X, and there we will have the 2 normal looking chromosomes. However, for option 2, we can have, again, a healthy person by taking the 2 non-normal options. So it would be this one and this one. Why? Because again, the piece that is missing here has just migrated here. So we're getting a net of 0. The genetic information on these 2 equal to 2 separate chromosomes. So we're not losing and we're not gaining anything here. So if we take these 2 chromosomes to get in one of the same gamete, we will be healthy because nothing is lost and nothing is gained here. However, we will still have to write that there is a translocation occurring and it has to be in numerical order, okay? But this will still be healthy. Remember, any translocation will be healthy. However, for option 3, it's different. Now, option 3 states that you will choose one of the weird chromosomes and then one of the healthy chromosomes. So not both healthy and not both weird, but one weird and one healthy. In this case, it will look something like this. And you can see here that we have a deleted part here, but it hasn't migrated anywhere because we're not choosing this big mega chromosome. Instead, it's just a deleted piece right here. And this is how deletion aberration occurs as well as insertion. We just have this deleted part. We can't find where it has migrated from because we chose the wrong chromosomes. And therefore, because this is technically a deletion, it will be unhealthy. There will be a deletion on the one that had the piece migrating into the other piece, right? So 23X deletion on number 9. Option 4 is the opposite. So here we chose the typical chromosome for number 9, and then number 8 we chose the one that had the piece inserted. However, now we we have an additional. Actually, technically, this piece is the same as this piece. So we have gained information here, because technically this would have been equal had this piece not existed. Then there would be an equal balance here. But now that this piece does exist, we have gained this thing right here, and therefore there's an insertion going on here, and it will be unhealthy because we're gaining something, and if we're gaining something, it's gonna be an unhealthy thing. So that's 23x, and then insertion on number 8, right? Because we're gaining something right here. Okay, those are all the options. It will always be like this. Always be like this. Even for deletion, it will only be 2 options. One without the deletion, one with the deletion. For insertion, one without the insertion, one with the insertion. For reciprocal translocation, it will be one that is completely healthy with no aberrations at all. One that has the translocation chromosomes, which means there's a gain of 0 and a loss of 0, so it's a net 0. This piece is just part of this piece, but together they form, 2 chromosomes. So this would be healthy. Option 3, there is a deletion because we only took the deleted chromosome, we didn't take the inserted chromosome, so that would be deletion, and that would lead to unhealthy. Versus option 4 would be insertion, we only took the inserted molecule, we didn't take the non-inserted, and this will be gain of a piece, which means it's an unhealthy karyotype. Final one is Robertsonian. Robertsonian doesn't have 4, it doesn't have 2, but it actually has 6 different gamete types. Now this one was a little bit more difficult to understand, but I will try my best to explain it. So imagine Robertsonian, remember that it means that we only have one single chromosome from a chromosome pair left. But the chromosome that was actually here migrated into the chromosome that is that has been accepting the migrated part. So therefore the net loss would be 0, and the net gain would also be 0. So this is actually healthy. This represents 4 different chromosomes, even though it's technically just 3. And the best way to explain it would be, imagine this one being represented with an A, this one B, and this one C. So you can either have, and you have to choose either 2 or 1 respectively. So you can either have AB, AC, BC, or just C, just B, and just A. Okay, those are your options right here for how you can split it in half, right? Because you can't just, again, remember gametes, you have half of your genetic information. But if there's an odd number, which is the case here, there's 45 instead of 46, the way you will split it would be either taking only 1 or taking 2. And these are the different combinations that you can do, which are 6 in total. Remember that, 6 different combinations in total. The first one is obvious. You skip this one and you just take this and this, which would give you completely normal and healthy karyotype. So you just took this and this, and you didn't take the one that has the very big forehead almost. For option 2, and remember here there's 22 instead of 23. So there's only 22 chromosomes. However, there's a Robertsonian translocation between 21 and 22. That means that makes sense. That means that the information is not lost nor gained. We have both information from 21 as well as 22. However, you can see here there are no chromosomes on 22. However, this chromosome right here represents both the chromosome here as well as the chromosome here, because it has not 1 but 2 chromosomes technically in its chromosome body. Therefore, this will represent 2 chromosomes in total. However, in our case, we will just, we're counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh yeah, I counted all right. 12, 21. There's nothing in 22, and then there's 1 here. So that would be 22 in total. So 22, right? But because we've technically lost this one here, it's not really lost, it's actually just added right here. That means that it's a healthy person. We've not lost nor gained anything here, and therefore we would have this type of karyogram. Even though we have 1 less chromosome, as long as we have a Robertsonian translocation between them, meaning that we have a chromosome that equals 2 chromosomes pretty much, nothing will be gained or lost, right? So as soon as you see something Robertsonian and it seems like it's 1 less chromosome than normal, then it will be healthy. Okay, remember that. As soon as you see Robertsonian and it's 1 less chromosome than normal, then it will be healthy. Meanwhile, here for option 3, let me just sit down more comfortably. For option 3, we have actually an unhealthy. The rest will be unhealthy or miscarriages, depending on which chromosomes are affected. But I picked 21, and I will explain why. So in this case, we have 23x Robertsonian 21, 22 plus 21. What exactly does this mean? Well, it means that we have 23 chromosomes in total, and it's Robertsonian. Meaning, remember what I said, if we have 22 Robertsonian, that means that we have an equal genetic distribution. There's no loss or gain. But now we have 23 Robertsonian. That means that we have an additional chromosome. And for us, it would be a additional chromosome on chromosome number 21, which is right here. Now, why this matters, and remember this would be BC, so it would be this type of assortment. You may ask yourself, well, how is it possible that we have 2 chromosomes on 21 when we're supposed to have 1 per chromosome pair, right? Well, the thing is that when the gametes are created, they're not thinking, well, we have to have 1 from here and 1 from here and 1 from here. They're not really thinking like that. They're thinking we're taking the ones that are different, and we're taking 1 of each, pretty much, is what they're thinking. So in this case, they're not seeing these 2 as equal, they're just taking 1 of each. So this is completely possible right here. And why this is bad is because technically this chromosome, like I said, represents not 1, but 2 chromosomes. So if we have an additional chromosome here that is actually a complete copy of this one right here, it will be bad for you. It will count as this being an extra, even though technically the gamete amount of chromosomes is an unhealthy amount, 23. But because one of them is technically has the information of 2 chromosomes and not 1, we are gaining something here. We have this 21 here, we have this 22 technically here, but then we still have an additional copy of 21 here. That's why we write plus 21. And if we remember trisomies, because this will lead to a trisomy, why? Because once we add, let's say the father's gametes comes in and he is completely orange. Forgot that this will take a while. But let's say that we are creating a zygote here. A zygote means that a sperm and an egg are morphing together, right? Very artistic. So then on 22 here, it's gonna add 2, or it's gonna actually add 1 here, I think, and 1 here. And technically this is 22 as well, so we will have 3 on 21, and that is a trisomy. Now, if we look up, the only trisomies which are viable for life, so unbalanced karyotype, but the only ones that are viable for life would be 13, 18, and 21. So these ones right here. And in our case right here, it would be a plus 21 trisomy. Not minus. Minus means it's a monosomy, and if we remember, monosomies are always leading to miscarriages. But trisomies, it's only these ones that don't lead to miscarriages. So if we look down here again, oh, that's an example. This would be a trisomy because it's plus, we're gaining something, plus 21, and therefore it will be Down syndrome. It will be born, but it will be unhealthy. So that's option 3. Option 4 is, why did I write it like that? It's better if I write it like this. I don't know what I'm doing. Sorry, guys. Trying my best here. Okay. Option 4 would be the opposite of option 3. So instead of gaining something, we are actually losing something. And how do we do that? Well, remember when I said there's different ways to assort these. So in this case, we would only have A in our assortment. So we're not having AB, not AC, not BC, we have a single A. And in this case, it would be this. So we're not taking any of these. Because remember, we can't just, when we're trying to take half of these, we can't just split this C into half and then give back one and the other one give back as well. Instead, we're taking either one or two of them, right? In this case, we're taking one. And that would be for us here. It would be the opposite of what we have here. Here we had an additional chromosome in 21. So it'd be a trisomy. Here we have lost 21 completely. And when we add in dads, so let me actually do this. So let's say we add in dads like this. Boop, 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 beep, bop, boop, boop. You can see here that we still only have one chromosome here. And this will not be viable for life because this is a monosomy. Now you may ask, well, didn't we have Robertsonian only one? Yeah, but Robertsonian, the other one, was translocated into another chromosome. In our case here, because we're losing, we're not taking this mega super duper chromosome with us. We're actually picking only this one. Because of that, we've lost a chromosome, and therefore it's a monosomy. We have a minus one chromosome in chromosome 21, which is here, and that will lead to a miscarriage or a non-viable child. Option 5 and 6 are just like option 3 and 4, only instead of us gaining from one of the chromosome pairs, we're gaining it from the other. So for this, in this case, it would be 22 because 22 is the other one that is affected. So here we would be gaining a chromosome in chromosome number 22. So you can see here we have chromosome number 22 here. You can say, well, we're not actually gaining anything because there is no chromosome here that is chromosome 22. However, remember, the chromosome 22 has technically migrated into chromosome 21 right here at the top. So this represents 21, this represents another 22. And in our case, because this has migrated into this, there's actually not one, but two chromosome 22 representations here. So that would also lead to a trisomy, because once the dad, let's just add in here, once the dad adds the chromosomes here, we would have not one, not two, but three representations of chromosome number 22. And therefore, if we have an additional chromosome in 22, will it be viable for life? Well, let's see. The only ones that are viable for life are 18, 21, or 13. The other trisomies will always lead to a miscarriage. So in this case, because it's not on 21, it's not on 18, it's not on 14, it's on 22, this will be an unborn miscarriage child. Unborn, a miscarriage, a non-viable miscarriage. Or it is okay, let's see. Non-viable for life, which will lead to a miscarriage. There we go. Option 6 is just like we did for option 4 when it came to option 3. Option 6 is just that we're losing a chromosome at chromosome 22. And how does that look like? Well, we're choosing just the 21 right here. We're not choosing the big 21 right here that represents 2. We're not choosing anything here. Instead, we're just choosing this 21. And therefore, we don't have an additional chromosome 22 here. So when the dad's gametes comes right here, there's only one chromosome here. And remember, if it's a monosomy, one less chromosome in chromosome pair number 22, then it will lead to what? Any monosomy will lead to a miscarriage. So any karyotype or gamete karyotype that will have one less chromosome will lead to a miscarriage. Those are the 6 options that we have for Robertsonian translocation. But do remember that it doesn't have to be specifically on chromosome pair number 21 and 22. It could be on 13 or 14. It could be on 15. It could be on 21 and 22. Also on Y, but we're not going to get to there right now. However, also remember that I only took from the perspective of a female karyotype. If it's instead a male karyotype right here, well, actually, let me do this so it's easier for me to share this later without deleting everything. If we instead had a male karyotype, say this one's Y, then we would not only have 6 options, we will actually have the double amount of options. So for option 1, we'd have 23X or Y. Option 2, 22X or Y, Robertsonian 21, 22. For option 3, 23X or Y, Robertsonian 21, 22 plus 21. Option 4, 22X or Y, minus 21, etc., etc. So there will always be an option of it having a Y instead of an X. So that would be the only difference in this case, because we can either have the X chromosome or the Y chromosome as our gametes. Same thing here for reciprocal translocation. Yes, there are 4 options technically, but you also have to take into account that it can be or Y here. You could write or Y here as well, and you will get the point. But as long as you remember that for females, they can only have the X variant, while for males, if they have a Y chromosome, they could either have the X or Y gametes. Okay, this one is a little bit more complicated, but it is important to mention. So remember when I said that Robertsonian can only affect 1 chromosome pair. It doesn't have to affect 2 chromosomes pairs. And how does this work? Well, one of the chromosome migrates into its pair chromosome, which would be like this. And in this case, it would be actually a little bit more complicated for the gametes. It wouldn't be as many as the 6 options right here. It would actually only be 2 options. Why? Because imagine it like this. You're taking only half of the chromosomes from a karyotype to create a gamete, right? So you can either have this, because this is the only one that's affected. It's not this and this and this, like we had with the normal Robertsonian, where it was this or this or this. In our case, it's only 1 chromosome that's affected, and therefore we would choose either to have it or to not have it. So in this case, it would be 23X Robertsonian 15, 15 plus 15. Why plus 15? Because it's a trisomy. Why? Because this piece right here represents another piece of a chromosome. So technically you have 2 15s right here. And if you add the dad's gametes right here, we would have 1, 2, 3 chromosomes for number 15, and that would be a trisomy. And for number 15, do we have a viable for life trisomy for number 15? It's trisomy 18, 21, or 13. No number 15. And the other trisomies will lead to a miscarriage. So in our case here, it would be an unborn miscarriage. But you can also choose to not have that chromosome right here, in which case, if we add the dad's chromosomes, right, like that, so, we will only have one chromosome representing number 15. And therefore, it would be number 15 minus number 15. And with minus one chromosome, that would equal to a monosomy. And we know that every monosomy is equal to an unborn miscarriage. Monosomy means we only have one chromosome in a chromosome pair later on when we develop this embryo, right? Okay, last question, last rule before we get into the questions and examples. I'm so sorry, guys. It took this long, but I really wanted to go into detail and hammer in some points. So number 9, non-viable gametes are not included in final calculations of a probability of a healthy children. So remember when I said that, for example, we take this as an example. So we have a healthy person right here, and then here we have a healthy person as well. And here we have an unhealthy person, so we just write a red check mark. But here, this person is unborn, so we don't count this as a viable option because this person will never develop into a born child, right? Same thing with this and same thing with this. So in this case, we only have 3 options for a child where one of the option is healthy and one of the options are unhealthy, Down syndrome, while 2 of the options would be healthy. We don't count the other non-viable to life options because technically they will not produce any child. They will just lead to miscarriages. So when they ask what is the chance for something to produce a healthy child, these are not viable options. These are. So be careful with that, all right? Okay, now we can finally get into some examples. Let me just bring up my phone so I'm not making any mistake. All right. Okay, I took away the arrows here, so it would be a little bit more tricky to understand what is happening. But this is a little bit easier of a starting example, okay? So let's start with the X and Y we can ignore, but this is important for later, characterizing the sex, but we can ignore when we're trying to look for what kind of chromosomal aberration it is, because this is not going to be important for our curriculum. These 2 seems equal length. These 2 kind of seems equal length, not really that sure. These 2 do seem equal. These seem equal. All 3 of these seem equal. All 3 of these seem equal to each other then, not to in comparison to from this to this, but to each other they seem equal, right? This 2, this kind of 2. This one looks a little bit wonky, but we're not that sure. This one as well. This one looks pretty equal. This one, even though it's kind of bendy, it looks pretty equal. This one looks a little bit like it's losing something there, but we're not that sure. We'll see for any more obvious examples. This one is very hard to distinguish. I would be very surprised if they added a deletion here that we had to be able to conclude. I don't think so. So I would often ignore these bendy ones. These, kind of, these one look pretty good. But then you get to this one right here. You can see that this one looks a lot smaller than this one, right? Even though this one is a little bit bendy, let's say we perk it up, it would kind of look like this. And would still lose this piece right here that this one has. So in this case, all other chromosomes look normal, even this one. But here it looks like something is missing from this chromosome. And that way we know it's a deletion on number 5. So That's important to write. Deletion on number 5. And to write the karyotype of the person, karyotype, it would be what? How many chromosomes do you have for deletions? You always have 46. You can count it as well if you want to. 46. Now what is the 6? It has both an X and a Y. So we write it down, X and a Y. And then we write a D for deletion, and then parentheses, then chromosome number that where the deletion has occurred. So right here, that would be 5. Is this a healthy or an unhealthy person? Remember, if we lost or gained information, additional information, it will be unhealthy. However, if it's a balanced karyotype, or a piece of information has just migrated into another piece, then we have healthy people. However, here, if we remember from our little notes, a person is unhealthy if there's deletions, insertions, or trisomies that are these specifically. So in our case right here, because it's just a deletion, it hasn't migrated anywhere else in this table, it has to be unhealthy because we've lost genetic information. Now we draw the gametes. So this will be interesting if you remember. So now imagine that we're only picking half, right? These are all going to be, we're going to be able to distribute these into halves, right? We either pick this one or we pick this one, but it doesn't really matter. Here we pick either this one that is healthy or this one that has the deletion. So let's write it down. We have two options. It's going to be 23 because it's half of 46. And then it's X, or be careful with the or Y, right? Because it can either have a X chromosome or a Y chromosome. And then we write deletion on number 5. In which case this person will be unhealthy. It will be born, but it will be unhealthy. Number 2 is just X or Y. And in this case, we're picking this healthy chromosome instead of the unhealthy. So this would be all that we're writing, and it would be a healthy person. Right there. Should I keep this for people to read? I guess I should, so that it's easier for people to calculate, I guess. Okay, that is the example here. There's 2 different gametes, and so what is the chance for people for a child to be born healthy? It would be 1 out of 2, because these 2 are viable for life. This is not a miscarriage, so we can count it in. This one's unhealthy, and this one's healthy, so it's 1/2 chance that the child is born like this. Next up is this one right here. We can immediately assess that something is missing here, right? But can we assume that it has been migrated into another piece? And if you see this chromosome right here, you can see that it is very asymmetrical. And it seems, if we compare to the other chromosomes right here, it seems that the normal length should be here and it shouldn't be up here. So here, there's probably been an insertion. So remember, just because you see something that has been deleted doesn't mean that there isn't an obvious migration that has occurred. And if it's migrating, that means we're looking at a translocation. And is it Robertsonian or is it reciprocal? Remember, Robertsonian, it would only be 1 chromosome left on either one of these, and we obviously have 2 chromosomes left. So in this case, it would be reciprocal. Okay. Wow, great. So for the karyotype, we would have, let me write it down. For the karyotype, we would have, sorry, we would have a total of 46 chromosomes. Remember, it's always 46 unless it's Robertsonian translocation, which would be 45. And then we will look at the chromosomes, or sex chromosomes. In this case, they have been a little bit cut off, but I've written them down. They will not be cut off, hopefully, in the colloquium. So XX, and it's a translocation between 2 and 9. So we will write T2, 9. So right there, right like that. Will this person be healthy or unhealthy now? If you said healthy, you are correct. Why? Because we're not losing and we're not gaining anything here. Instead, we're just migrating. This little piece has just migrated into this little piece. So in all, this person will have a healthy life, comparatively. So in our case, he has healthy because he hasn't gained or lost anything. Now for his gametes. If you remember, reciprocal translocation always has 4 different types of gametes, but let's write them down off the top of our head. So number 1 is the normal type. That means that we're only taking the normal looking chromosomes, this one and this one, into account when we're splitting it all into 2, right? So the normal one would be 23X. And remember, only X, not X or Y. Why? Because this person only has 2 X chromosomes, so there is no Y. Okay, number 2 would be, or in this case, this person would be, of course, healthy because there is no issue. Number 2 is if you take the 2 chromosomes that are the weird ones or the affected ones. So it would be this one that has the insertion and this one that has the deletion. So let's write it, and actually the translocation, right? So let's write it down, 23X T2 9. So we would only take this one, and we know that it's translocation because this piece has migrated down to this piece. Will this person be healthy? Remember that if you have translocation, you will be healthy. Why? Because one piece of the chromosome has just migrated into another piece. So if you have both of these, it'll be fine because you're not losing or gaining anything. So in our case here, this will be a healthy child as long as there are not any other complications, but we're not counting that in. Number 3 is if we're taking one weird and one non-weird chromosome. So let's say we take this one and this one. This one is the non-weird one. This one is the weird one. So in our case, if we don't have this, that would compensate for the lack of this little piece right here. We only have this and this. We're actually dealing with a deletion here. There is a deletion of this piece and it hasn't migrated anywhere because we're taking this instead of this now. So in our case here, we would write 23X deletion, and it would be a deletion in number 2, right? Number 2. Would this be healthy or unhealthy? This will, of course, be unhealthy. Why? Because we're losing genetic information. Number 4 is the opposite of this. So in this case, we would take this chromosome that is abnormal and this chromosome that is normal. And because we have a normal chromosome here and then we have an abnormal here, we only really need this, but we have this inserted. This is an additional piece. That means that there has been an insertion here and we can't compensate it with the lack of something here because we're choosing this instead of this. This one is out of the picture now, which we've chose this and this, right? And now we have gained genetic information. So it will be insertion on number 9, and it will be leading to an unhealthy child. Why? Because we've gained a piece right here. because we're not compensating it with this. This one and this one is out of the picture. We're taking this one and we're taking this one. So those are the options. That's just as easy as this translocation thing goes. Oh yeah, if they ask the number of healthy children, in this case, it would be half. So 2 is healthy, 2 are unhealthy, so it'd be 1/2 that are healthy. It's actually a normal, okay. So when we're dealing with deletions, insertions, and reciprocal translocation, not Robertsonian, but reciprocal, the amount of healthy children will always be 1/2. So if you're doing it right, you will always have 1/2 healthy children. But you still have to show how you got there. So it's not enough for you to just write 1/2, right? Okay, number 3. We are dealing, oh, look at this. This is a single chromosome. And if we see a single chromosome, it can't be a monosomy because that can't be a born person. It means that this chromosome has migrated into another chromosome. And if it's and of course it's Robertsonian in that case because we have a single chromosome, and for Robertsonian it only works on chromosome 14, 15, 13, 21, 22, and Y. So we're not looking at any of these are out of the picture. You can see that this chromosome has probably migrated into this 14 right here because it has this additional big forehead. So now we know that 15 and 14 is what is affected. So we can write down the karyotype. Well, let's actually first write Robertsonian translocation. And how do we know that? That's because we have this single chromosome right here. The karyotype, and remember for Robertsonian, we're actually dealing with 1 less chromosome because there should be a chromosome here. So instead of 46, we're dealing with 45. And what is the 6? It would be 2 X's, so X. And then we're dealing with Rob, parentheses, and the 2 chromosomes that are affected, which is 14 and 15. So here would be 14, 15, end of parentheses. Now for the gametes, and if you remember for Robertsonian, there's always 6 different types of gametes. 5 and 6. Okay, the first type is of course normal. Why? Because you can choose to have this normal one and this normal one and ignore to have this. So in that case you would have 23X, just normal, because you have one for one pair and one from one pair, and ignoring the weird one, right? The weird 2 chromosome merged together. For number 2, sorry, this would be you having just this one. Why? Because this represents 15 and this represents 14. So this is just a balanced net 0 chromosome that we have. If we just pick this one out of all 3 of these, we're still going to have it balanced because technically we have both 15 and 14 here. So let's write it down. It would be 22. Why? Because we only have 1 chromosome here. We're not taking this one and we're not taking this one. So it would be the normal minus 1, so 22. And then we would write X. And then we would write Robertsonian translocation because it's technically still Robertsonian translocation. So it would be Rob. And it means that 15 went to 14. So 14, 15 right here. Because we have to write it in numerical order, not in the order of which one went to which one. Okay, 3 would be if we picked, for example, these 2 and not this one. In our case here, we would have 2 that represents 14, so we would have an additional 14. So if we write it down, 23, because it would be 23 chromosomes, because we have 2 here and no here, so technically this will be equal to 2 chromosomes, which is normal for gametes. So it would be normal amount of chromosomes, 23, X, Rob, 14, 15, because we still have this monstrosity right here. But we will have plus 14, why? Because we have picked this one as well. So it would be plus 14. And in this case, this would be, oh no, this is not Edwards. Oh wait, is it Edwards? Is it Pateau? I think it's Pateau. Oh, it's not even Pateau. Pateau is 13 and Edwards is 18. So if we have a plus 14, that means that it's a miscarriage. So this one is not viable for life even. Right here. So this would be miscarriage. Okay. For this one right here, we would have a would this one be healthy? Yes, because we have a, if we again go back to that one, oh, and there was the spoilers. We pick this one and we don't pick any of these ones. This one still represents 15 and this one represents 14, so it's an equal amount of genetic information. We're not gaining and we're not losing anything, which would be healthy, right? Well, this one would of course be just a healthy child. Number 4 is if we had this, but we actually lost a chromosome. Now, how would that look like? We had the Robertsonian, no, sorry. We only pick this one. We don't pick any of these ones. So in this case, we would have 15, but we don't have any of the 14. So it would be 22X, because again, there should be a chromosome here, but because they're not, there's going to be one less chromosome, so 22. And then there's not a Robertsonian translocation because we picked this and we picked nothing here. So no Robertsonian translocation, instead we just write minus 14. And because this will lead to a monosomy, why minus 14? Because we don't have anything of 14, so minus 14. This would lead to monosomy, which would be a miscarriage. Miscarriage. Number 5 is the same, only with the number switched from 14 to 15, and I'll show how that looks like in a second. Let's just write down exactly like this one. 23x Robertsonian 14, 15 plus 15 instead of plus 14. So how would that look like? That means that we have an addition of 15. So we would pick this one and not that one. So this would represent 14, this 15, but also this 15. And therefore we would have 2 15s in one gamete, which is not good. We're supposed to have one of each. So that would be a trisomy 15. And if we remember, would this be viable for life? Trisomies are only viable for life if it's on 18, 21, or 13. Because this is 15, this will be not viable for life, i.e. it would lead to miscarriage. Whoop. Carriage. For number 6, it's the same as we did up here with 14. So 22x minus 15. And of course, it's a monosomy. So that would lead to a miscarriage. And let's look up here how that would be represented. That's if we take that and not this one nor this one. That would be a minus 15 because we don't have anything representing 15, therefore minus 15. Okay, now what are the chances that the children born will be healthy? So it will be healthy right here, it will be healthy right here. Here it would be a miscarriage, here would be a miscarriage, here and here. So out of the children born, and be careful here, 100% will be healthy. Why? Because the miscarriages aren't counted in as children born. What are counted in are the born children, which in this case would be only these two options. So 100% of them, because we're only looking at these two options, because those are the only ones that are going to be born, are going to be healthy. Isn't that cool? A lot of miscarriages though. Okay, number 4. We can see immediately. If you can see it, kudos to you. But in our case, boop, 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 boop. I'll just make sure that I can see it and I'm not making a mistake. Yep. So you can see right here that there is a single chromosome on number 22. And this chromosome, and it's a little bit harder to see, so I think in this case they would add in an arrow for us to understand. But the chromosome that was normally here actually migrated here, because this top one is actually a lot bigger than this one. So in our case, because we're saying only one single chromosome, we know for sure that it's Robertsonian Translocation. 100%. Now the karyotype for this person, karyotype, would be one less chromosome, because we're dealing with one less chromosome here, even though technically the genetic information is there. So it would be 46 minus 1, so 45. And then it's X and Y, so XY. And then we write Robertsonian between 21 and 22, right? 21 here and 22 right there. So now we write, well, first actually we're supposed to see if this person will be healthy or not unhealthy. Remember, you're healthy if the genetic information hasn't been gained nor lost. If it's a balanced karyotype, you're unhealthy if it's unbalanced. Something has been gained and something has been lost. In our case, nothing has been gained nor lost because the little chromosome here has just migrated into the chromosome head right here. So in our case, this will be a healthy person. Nothing is gained and nothing is lost. For gametes, there are, again, because it's Robertsonian, there are 3 options. 4, 5, 6. Now remember, trisomies, I think it's 13, 18, and 21. Yeah. Trisomies can only be viable if it's 13, 18, or 21. Plus 13, plus 18, and plus 21. Okay? So let's look at the first one. The first one, of course, if we choose the health, let's delete this. We choose this one, the normal one, and the normal one here. We don't choose this one. That means that we're going to have an equal distribution, i.e. 23x, or, and remember the or y, because you can either get the x or the y from your dad. Number 2, so, oh yeah, this will of course be healthy. Number 2 would be another healthy option, but I'll explain why. And that is if you only take this and none of these. Why? Because this represents 21 and this represents 22. So you're not gaining nor losing anything here. But technically you have one less chromosome because you have nothing that would represent 22 directly. So it would be 22 because 23 minus 1 is 22, x or y. And that is going to, of course, Robertsonian between 21 and 22. You have to write that down for it to be healthy because that represents this megaloth right there. And that would be healthy. Okay, number 3. Now we come to the juicy stuff. Have to excuse me. Okay, 3 would be a... if we take, for example, this one and this one, but not this one. So because we have 21 here and 21 here, these 2 will be excessive, or one of these will be excessive. We don't need 2 of them. That would just add to a trisomy. So in our case here, it would be 23 because technically we have 23 chromosomes if we count the gametes, X or Y. And then we would have a Robertsonian because we're counting with this one. As soon as we write Robertsonian, we make a we flag for the fact that this behemoth is here. So Robertsonian 21, 22. And then we would have a plus 21 because we have an additional information that we don't need because the 21 is here as well. And it doesn't have to be here, or else it's plus 21. And this is a trisomy, so let's look if it's viable. We can have it viable if it's 13, 18, or 21. Let's just double check here for you guys to see. It's viable for life if it's Edwards syndrome, which is plus 18, plus 21, or plus 13. In our case, it would be plus 21, and that's Down syndrome. So it would be unhealthy. However, good news, it's still viable for life. Okay, next up would be that we're actually losing 21. So let's see here. It would look something like this. So we're choosing this one over these two. So we don't have anything representing 21. So in our case, it would be, we have one less chromosome because, you know, we don't have anything representing here. And then it would be X or Y minus 21 because we don't have a 21 here. And because it's a minus, it always leads to a miscarriage because it's a monosomy. Number 5 would be the opposite, only instead of 21, it would be 22. So up here it would be 23 X or Y, Rob 21, 22 plus 22. And then down here it would be 22 X or Y minus 22. And I'll explain exactly how that would look like. So plus 22 with Robertsonian would be you're picking this and you're picking this, but not this. So you have an additional 22 because technically this one also represents 22. So that would be plus 22, right? Meanwhile, minus 22 would be if you just pick this one, not this one or this one, then this would be technically minus 22. And of course, if it's minus, it always leads to miscarriage. Always leads to miscarriage. But if it's plus, it leads to miscarriage unless it's one of these three. So 13, 18, and 21. In our case, it's neither. So this will be a miscarriage as well. So in our case, what are the chances that these will produce healthy children? Excuse me. So we don't count with none of these miscarriages because these will not produce any children at all. This one will be unhealthy, this one will be healthy, and this one will be healthy. So out of these three options, 2 will be healthy. So we write 2 out of 3 healthy. That's just how easy that was. Next up is number 5. Boy, we have a long way to go. Okay. So number 5 is dealing with what exactly? Well, we can see here a single chromosome here, and this chromosome has probably morphed together with some other chromosome. 13. You can see here 13 normally looks this small, and then all of a sudden it gets this big. It looks like this chromosome right here just migrated up here. So so let's write down Robertsonian Translocation, and we know immediately that Robertsonian has 2 different or 6 different types of gametes. Number 21 and number 13 is what is affected. So the karyotype, the karyotype would be 46XX, right? Because 2 X's. And then Robertsonian on number 13 and 21. So 13, 21. Okay, now gametes. There are 6 in total, like I said. 3, 4, 5, 6. 6 in total. The first one is gonna be healthy. Why? Excuse me, I'm yawning a lot. The first one would be healthy. Oh God, it's midnight. Okay, the first one will be healthy. Why? Because you can choose this one and this one, and not this big behemoth right here. So it would be 23x, okay, just x, because we only have x to choose from. The second one will also be healthy, however, it will be the opposite. So instead of choosing the two normal ones, we're not going to choose them, and we're choosing the one big behemoth, because this one represents 21, and this one represents 13. But it would be one less chromosome, because, you know, we can see here that we technically have one less chromosome here. But the chromosome information stays the same. Why? Because we have the big merged one. So X, Rob, 13, 21. Okay. Next up is if we choose these two, right? And in that case, we would have 13, 14, and 13 again. So we would have an additional 13, but 23 chromosomes. So X, Rob, 13, 21 plus 13. And plus 13, we can look up here. That is Pateau syndrome, I think. Now I have to double check that it's Pateau. Yep, Pateau syndrome is plus 13. So in our case here, we would write it as Pateau, and that is unhealthy. An unhealthy kid. How would you suggest write it? Yeah, you know nothing. You know nothing, good notes. This would be an unhealthy child, of course. Number 4 would be the opposite. So if we chose this and this, but not this. Oh, sorry. If we chose only this, but not this nor this. Let's actually do the opposite here. Sorry. That will come later. If we choose only this, but neither this nor this. And that would lead to 22x minus 13. Why? Because we only have one here, but we have no chromosomes that represents that there. So this will be miscarriage, because anything that's minus leads to a miscarriage. Number 5 will be the opposite, but instead of 13, it will be plus 21. So here would be 23x Rob, 13, 21 plus 21, and that's Down syndrome. As you can see right here, 21 is viable for life. And it's down, so it will be unhealthy. While number 6 will be 22x minus 21, and this will lead to a miscarriage. Yeah. Oh, well, not yeah. It's not good to, you know, miscarry, but I'm just happy that I'm done with it. That's all. Okay. And how will this one look like? Well, it will look like something like this, where we have this, not that, but that. So we have 13 represented here, then we have a 21 here, and then an additional 21 here. So we will have plus 21. Well, here would be minus 21, which means we only have this and neither of these. So that would be minus 21. Okay, next up, number 6. This one is from e-studies, actually. Let's hope I made it correctly, because I didn't go through this with my professor. So here they've added the arrow, and it says something like this. Now we know that this one has something inserted. It looks like this one's just a little bit bigger. But is insertion all we see in this whole karyogram? If you say no, you're correct. Because here you can see that 22 is very lonely. And if it's lonely, you immediately know we're dealing with Robertsonian Translocation. And the karyotype would be right here, karyotype. Oh, how am I writing? Type. Karyotype would be sorry, one less chromosome. And where did this chromosome go? It went right here where the arrow points. So right here, that's where it went. It just migrated here. So this person is completely healthy because there's no loss nor gain of information. But let's write down their karyotype, and it will be one less chromosome because technically they have one less here. So it'd be 46 minus 1, which is 45. And then XX, because that's the only chromosomes they have, XX. And then we will write Robertsonian on the 2 affected ones, which is 13 and 22. 13 and 22. And this will be a healthy person because they have a healthy distribution of information. Nothing is gained nor lost in terms of chromosomal information. I need to go to bed as soon as possible. Okay. Gametes. If you remember for Robertsonian, there's always 6 gametes. Oh, did we write? Oh, we didn't do... Oh, sorry, we didn't write the probability for healthy children up here. So probability for healthy children here, we know that this person will be healthy, and this person will be healthy because it has the Robertsonian and no extra 13 or 21 chromosome. That would be pato, unhealthy. This would be miscarriage and miscarriage. So probability for healthy children, and we don't include miscarriages because those are not even viable for birth. It would be these 2 healthy, this pato, and this down. So that would be 1 out of 2 healthy. Right? Okay, next up right here. This one is what we just went with. Sorry, the first one will be the normal type, so we take only this one and this one, which are the normals. We ignore completely the Robertsonian one. So in that case, it would be 23X, and that would be, of course, healthy. Type after that would be the Robertsonian example, so that's if we take this, but we don't take neither of these. And why is that important? Because this one would represent 13 just fine, and this one represents 22 just fine. So in that case, we would write 22, because there's 1 less chromosome. Here, there's none that represents 23. That would be X, Rob, 1322, because the Rob 1322 means that we have this big behemoth of a guy. And that would be healthy because we're not losing nor gaining any genetic information. It's balanced. Number 3 would be if we're gaining information. So for example, let's say we have these 2, but we don't pick this. And that is bad because why? We have 1 copy of 22, but 2 copies of 13. So in our case here would be 23X Rob. And remember, if we have normal karyotypes with Rob, it's not a good sign. It's not at all a good sign. 22, and this would be plus 13, which if you remember from before, that's going to be pato. Plus 13 is pato. Pato, pato. Let's just say it's spelled like that. Number 4 will just be losing 13, so it would be 22. Let's actually show it here. So we only took 22 and we got rid of this. So it would be 22X and then minus 13. And that is going to be Y22 because we're losing a chromosome, right? And that would be a miscarriage. Why? Because it's minus and it's a monosomy. Not and, but it's a minus, therefore monosomy, therefore miscarriage. 5 is just the opposite, but instead of plus and minus 13, you write plus and minus 22. So let's write it up here. X Rob 13, 22 plus 22, and then 22X minus 22. So in our case right here, that would look something like this. We're picking these 2. And why is it an additional 22? That's because we have a 22 here, and we have technically a 22 up top there, and just 113. However, is this still viable for life? Remember, the only viable for life ones are 13, 18, and 21. This one's 22. So in our case, this one will be a miscarriage. Why did I sound so happy when I said that? I don't mean it in a happy way. Okay, 22 minus the chromosome at 22. How would that look like? Well, it will look something like this. So we don't have this nor this, and we have just this healthy one at 13. So we've lost 22. That is, of course, monosomy, and it leads to a miscarriage. Okay, now to calculate the amount of healthy, we ignore the miscarriages because they will not be children. And this one is also a miscarriage. And then we check just these three right here. And it's 2 healthy versus 1 unhealthy. So 2 out of 3 healthy right here. Okay, number 7. This one's from E-Studies. You can see again here, it's just 1 chromosome, so it has to be Robertsonian. So let's write Robertsonian. And they gave us the pleasure of showing which chromosomes are the ones that are going to be affected. So 21 and 14. So when we write the karyotype, we write 45 because it's 1 less chromosome. And then it's X and Y right here, so XY. And then Robertsonian on 14 and 21 in numerical order. Now the gametes would be again 6 in total. 2, 3, 4, 5, 6. And remember, we can pick the normal ones, so this one and ignore that one totally. And that would be 23X or Y, because we have a Y chromosome as well. However, we can also do the opposite, in which we just take this one and ignore this one and this one. And because this big behemoth represents both 21 as well as 14, this will be enough for this karyotype. So it would be 22 because we don't have a chromosome here. And then X or Y, and then we have to write the Robertsonian 1422 to represent the behemoth right here. Next up is number 3, and that was going to be plus or minus. So let's say we take both of these, but not that. So that's going to be 23X or Y. And then Robertsonian does exist, it's right there. It's going to be 1421. However, this chromosome right here represents 14, just as much as this chromosome represents 14. So we have an additional 14, and 14 is that part of the healthy ones. No, it's just 13, 18, and 21. So in our case here, 14 will be miscarriage. 4 would just be the opposite of this. So minus 14, so 22 minus 4, 22, X or Y minus 14. And if we look here, that would look something like this. Is it 22 or is it 21? Why did I write 22 so far? Oh, that one is 22, yeah. Yeah, I wrote it correct. I don't know, I'm just tired, I guess. Yeah. So here we would have minus 14, so we would only have this and none of these. So we're losing 14, therefore this is going to be a monosomy, which means it's going to be a miscarriage. 5 is the opposite way around. That's going to be that we have an extra 21. So this one we keep, that one we don't keep, and this one we keep. So this would represent 14, this would represent 21, and this would obviously also represent 21. So we have an additional 21. So 23X or Y, Robertsonian 14, 21 plus 21. And that's going to be Down syndrome, unhealthy, right? Unhealthy. Well, number 6 is going to be the same as this one, just with the minus 21 instead of minus 14. So X or Y minus 21, and that's of course going to be a miscarriage. And in that case, how minus 21 looks like would look like something like this one and this one. That's how it would look like. Okay, how many children will be healthy? Let's ignore the miscarriages because that's no born child. So the amount of children born healthy would be these two because none of them are losing nor gaining genetic information. This would be unhealthy because no, that's also a miscarriage. Sorry, it's 14 plus, not 13. So actually, we would only have one unhealthy option, which is this Down syndrome right here, out of a total of 1, 2, 3. So 2 out of 3 healthy. Perfect. Number 7.5 is a little bit difficult. This is what I talked about in the 4.5 rule, I think it's called. Yeah, 4.5 Robertsonian Translocation, where a chromosome morphs together with its own chromosomal copy. And the signifier would be a lone chromosome that seems larger than its neighbors, for example. So let's go down here. Number 7.5, I'll already spoil it to you. That's Robertsonian translocation because, again, it's a single. That would be easy to tell. However, the chromosome that was here actually immigrated to this chromosome, creating this behemoth right here. And in our case, if you remember from the rules, up here, Robertsonian translocation gametes, only one chromosome affected. There would only be two options. There would be one option that has the additional chromosome, or this behemoth, which represents 1 and 2 chromosome 15s, because this one, migrated here. Or we don't have it at all, and then we have a monosomy, which is also leads to miscarriage. So let's look at her right here. This would be Robertsonian, right? And we would have a karyotype of 46 minus 1, which is 45, X and Y. And then Robertsonian 21, 20. Oh, sorry. Robertsonian is 14, 14 because the 14 that was here migrated into the 14 that was there. So in our case, that would be 14, 14. And would this be healthy or not? Well, we're not losing nor gaining any genetic information. It's just stored right there, so that would actually be healthy. Well, here, genotype. What am I doing in my head? Gametes. 1, 2, 3, 4, 5, 6. Gametes, oh sorry, it wouldn't be 6, it would only be 2 because this only affects one chromosome. It's not a normal Robertsonian translocation. So we either have this one, that means that we're going to have 23, an additional chromosome, or a normal amount of chromosome, but because this one represents 2 chromosomes in one, it's going to be an additional chromosome. So 23, and then it would be X or Y, Robertsonian 14, 14, then plus 14, because we have 2 14s. We have this 14 and this 14. Okay, 2 would be if we don't take this one. So if we don't take it, we're going to actually have a monosomy because we have an empty slot here. So it would be 22X or Y minus 14. And that would be a miscarriage. What would be plus 14? If you remember, the only viable trisomies or pluses are Edwards syndrome 18, 21, and 13. So let's look down again at what I had right here. 14. So it's neither 13, 18, nor 21. And this would be a miscarriage because any trisomy that isn't 13, 18, or 21 leads to a miscarriage. While this one also leads to miscarriage because it's a monosomy. Or it's, yeah, monosomy. And the two options you can see here all lead to miscarriage. So the chance for this person to have a healthy child will unfortunately be 0. Okay, here's one that is from eStudies. Let's see if I can do it. So immediately you can see that something is lost here, but can we locate it somewhere else? And you can indeed, it's actually right here. So this piece has been transferred here, right? In our case, this would be just normal reciprocal translocation. Why is it reciprocal translocation and not Robertsonian? Because there are 2 of each chromosome here and here. If it would have been if it would have been Robertsonian, what am I doing? If it would have been Robertsonian translocation, there would only be 1 chromosome here. Okay, so the karyotype is one less, or not one less chromosome, the normal amount of chromosomes, so 46, and then X and Y, so XY, and then the translocation, and then the 2 chromosomes are affected, so 9 and 22. 9 and 22. And now for gametes, that would be 23 X or Y. So that would be that you're either taking, oh, now you can see the spoilers, right? You're either taking this one or and this one, so the 2 normal ones. So that would be that. First one. Second one, we actually have 4 if you remember for reciprocal translocation. Second one would be if you take the ones that are equal to one another, so that one and that one, they're equal because this part has just migrated here, so we're not losing nor gaining anything. So that would be 23X or Y T922 because there's a translocation from this to this. And this would be healthy because, again, you're not losing nor gaining anything. And this would also, of course, be healthy. Now, next one would be, let me just write it down, 24X or Y. There would never be 1 less chromosome unless we're dealing with Robertsonian translocation. Next one is if we only, for example, took this one, now that one, and this one, and not that one. That would be a deletion in number 9, so we would lost that without any way for it to migrate to the next because we're taking away the migration part. So that would be a deletion on 9, and that would of course be unhealthy because we're losing genetic information. Meanwhile, the other way around, if we instead took this one and not that one, nor that one, nor, or well, actually, not that one, but that one, this would be an insertion because we have an additional piece right here in addition to the normal 22 chromosomes, so that would be an insertion in 22, and that would also be unhealthy. So in this case, the number of healthy children will always be 1/2. Again, like I said, in reciprocal translocation, in deletion, and insertion, the number of healthy children will always be 1/2. How many do we have left? Oh God, we have a lot left. Okay, let's zoom through these. Okay, we're gonna zoom through these a little. Number 9. So here we can see that we're dealing with some sort of a translocation. Why? Because we have a normal type of normal type of chromosomes. We're losing a piece here, so this one has migrated somewhere. We can see that it has migrated here because these should be equal length, right? So it's reciprocal translocation. So the karyotype will be, of course, healthy because we're not losing nor gaining anything. There's just a migration going on. The karyotype will be 46 xy, xy, and then t apostrophe or parentheses 4, 17. And then the gamete will be one of or 4, or there will be 4 options. 3, 4. I think I'm too tired to go on, so I'll just do I'll finish these in written form later, so we don't have to go through them, but these will just be repetitions of what I've done before. So I'll finish these later in written form, but I'll just do 9 and 10 for now. So I think 10 is enough for you guys. Anyways, there's different types of gametes. There's 33X or Y, which will be healthy. Also, this person will be healthy because they're not losing nor gaining anything. Also, there can be 23X or Y, and then with the translocation 4, 17. How does that happen? That means that we don't have this chromosome, nor do we have this chromosome. We only have this and this, but these balance each other out. The piece that is missing here is gained here. So there's no information gained nor lost. So that would be healthy. So next one would be X or Y. Actually, both of these would be 23X or Y. And here it would be that you're picking one abnormal and one normal. So in this case, you would be picking this, which is the abnormal one, and this, which would be normal one. So in our case, that would be deletion. So deletion in number 4, because we have deleted this, and it hasn't migrated here. It actually migrated here, but we have not picked this chromosome. So therefore, it's just a simple deletion. And then we have the opposite that is true. We can pick this normal one, not that one, and not that one, but this abnormal one. And here we have insertion instead of deletion. So that would be I-17. This will be unhealthy because there's a deletion or a loss of information. This will be unhealthy as well because there's also a loss of or a gain of information. So in this case, there's 2 unhealthy options, 2 healthy options, and that's 1/2. Next up, okay, perfect. This is Robertsonian Translocation. So I like to end it with this one because Robertsonian is always a little bit tougher. Why is it Robertsonian? Because you only have 1 chromosome here, so you know it's Robertsonian Trans. And what is going to be the person's karyotype? Well, it's going to be 1 less chromosome because we only have one here, so 45 instead of 46. And then we have X and Y, so XY. And then we have the Robertsonian translocation, and it is between 13 and 14. It's hard to see, but it's definitely 14. And this has migrated to this, because this usually would just be this tall, but it's taller, so therefore there has been a migration of information. So Rob 13 and 14, and it also works because Robertsonian translocation can only occur for 13, 14, 15, 21, 22, and Y. So it makes sense. Okay, now for gamete, or actually this is going to be a healthy person. Why? Because they haven't lost nor gained any information. They've just switched the information in how it's structured. So gamete, there's going to be, of course, 6 different options for gametes. 4, 5, 6. The first one is going to be a healthy 23X or Y. Why? Because you can choose to not pick the unhealthy one. You can just choose to pick these 2. That would be that. Or you can go the opposite way and pick this one instead of these 2. And this one, of course, represents 13 as well as chromosome 14. But it will be 1 less chromosome technically. So 22 X or Y, and then Robertsonian 13, 14. If you just pick that. Now we can also pick one that, so let's say we pick these two and not that one. That means that we have additional 13. So we have one here as well as one here. This one's 14. And that leads to a trisomy. So let's write it down, X or Y. And then Rob 13, 14. And then there's an additional piece on 13. Now let's see if that's viable for life. The only trisomy is viable for life is plus 18, 21, plus 13. So it is viable for life, plus 13 that is. And in our case, sorry, plus 13. In case it would be patho unhealthy. But this person would be healthy. And this person would of course be healthy. Okay, number 4, we just take, oh sorry, X or Y, I forgot. Minus 13, how would that look? Well, it would look something like picking this but not these, right? So that would be minus 13, and that is a monosomy, and monosomy always leads to miscarriages. 15, or 5, I mean, Jesus. 5 would be the same, only we switch this 13 with the other, which would be 14. So 23X or Y, Rob 13, 14, plus 14. And plus 14 is not viable for life. You can see it in the list here. The only ones viable for life are 18, 21, and 13, so not 14. So that would lead to a miscarriage. 10. So that would lead to a miscarriage. So write miscarriage right here. And then of course we have a miscarriage there. So finally we just have X or Y minus 14 instead of plus 14. And that would also of course leads to miscarriage. So the ones that are miscarried are this one, and this one. So that leaves only 3 options. And out of the 3 options, 2 are healthy and 1 is unhealthy. So 2 out of 3 healthy right there. Number 11, 12. 2 12s. And 13 and 14 I will write in the answers here, so you guys can look through it, but it's the same principle over and over and over again, okay? I hope you guys enjoyed. I really need to go to bed. Good luck on Colloquium 2. This will of course be the last video I do on Colloquium 2. So what is for Colloquium 2? It's both this karyogram or identifying karyograms. That's going to be 2 questions in regards to karyograms. And then the 3 questions would be about calculating for pedigree trees with the use of markers, okay? So if there's one video I did on that, and then there's this video, and that is all. So I hope you guys enjoyed. See you next time. And yeah, good luck on your colloquiums.